Words about ICTS. ICTS is a multi and interdisciplinary center with three main goals. So the first is research. So ICTS contributes to research excellence in theoretical sciences with its faculty along with a large floating population of visitors, postdoctoral fellows and students. And the second is programs. So ICTS has a lot of programs which aims to bring together researchers from all over the world under one roof to work together to solve the most challenging questions posed by nature. And the third is outreach. So outreach aims to take the science that we do into the public. So the Kaapi with Curiosity lecture series falls under outreach. So Kaapi with Curiosity is not the only way you can engage with ICTS. There are a lot more programs. In all the three respects you can associate with ICTS. So please scan the QR code to learn more. And yeah, so now I hand over the mic to the director of JNP to officially welcome.
Respected Professor Raghuram and ladies and gentlemen, welcome to yet another lecture under the Kaapi with Curiosity series. And you all know that it's a joint endeavor between Jawaharlal Nehru Planetarium and International Center for Theoretical Sciences. And, just a few words about Jawaharlal Nehru Planetarium. Jawaharlal Nehru Planetarium has its goals. As one is two goals, main goals. One is science popularization. We have umpteen programs for science popularization, including our sky shows and many seminars and lectures and such things. Yesterday, to tell you, India's second man to go to space, Mr. Group Captain Shubhanshu Shukla, and another Gaganyaan astronaut, Prashant Balkrishnan Nair, as well as Ravish Malhotra, who was the backup to Rakesh Sharma way back in 1984. They were all there here in JNP, and there was a book release. So like that, we have a lot of science popularization programs. One of them is this, of course, giant program, Kaapi with Curiosity. And the other thing is non-formal science education to strategize, to inspire students towards research from the elementary level till undergrad level. We have programs called Seed, Sow, and REAP programs. So like that. So all our programs, anyway, our QR code also is there about our YouTube channel and such things. Kindly do attend to all our lectures and all our programs. Kindly, this is for the general public we are arranging. And so I request you once again to kindly attend our programs. And once again, let me, on behalf of ICTS as well as JNP, let me welcome Professor Raghuram. And it was, one thing is, I saw his name, but I didn't sense. I came to know that we have come from an institution which is an extraordinary one. Not only for imparting education, but for molding the characters of the people. National Education Society, National College. So it was very nice to know that he's also from my area, only Baswangudi area. And the other thing is, now he's based in New York, that is different. And the other thing is, I was very pleased to know that his father was my senior colleague in Indian Space Research Organization, Dr. Anantram. He was a pioneer in propulsion systems. Okay, so it is very nice. So he is speaking on a very interesting subject. So circles and formulae and curiosity. Okay, so at least I learnt about pi when I was in school. He also says the same thing in the synopsis. And only in the next letter, Greek letter, what I learnt was after high school only, theta, alpha, beta, gamma. Okay, but anyway, all of us know pi. Okay, so anyway, I don't want to preempt anything, sir. The stage is yours, please. Thank you very much.
Welcome everyone. So on behalf of ICTS, I welcome all of you. Today, Professor A. Raghuram from Fordham University has kindly agreed to give our KWK. So Raghuram grew up in Bangalore, as was said earlier, studying in Kendriya Vidyalaya, ASC, till 10th standard. And then he did his PUC at National College, Bhavana Gudi. He went to IIT Kanpur for a BTech in computer science and engineering. And for his doctoral work, he studied at Tata Institute of Fundamental Research in Mumbai. As a professional mathematician, Raghuram is a number theorist and a leading expert on special values of L functions. He is currently a professor of mathematics at Fordham University and previously has been the head of mathematics in that department, in the Department of Mathematics at Fordham University and the Indian Institute of Science and Education, Indian Institute of Science, Education and Research, Pune. Raghuram is a fellow of both the Indian Academy of Sciences and the Indian National Science Academy. He has been a frequent visitor of the Max Planck Institute for Mathematics at Bonn and a member of the Institute for Advanced Studies at Princeton. He was a recipient of the Alexander von Humboldt Fellowship, and most recently he was awarded the prestigious Simons Fellowship, based on which he will be a member of IAS Princeton for 2026 to 2027. Raghuram is an avid runner and has twice run the Bangalore Marathon. Before he starts, there's a small memento for you from ICTS.
Thank you very much.
So, over to you.
Okay, thanks a lot. We were so excited catching up and getting to know that sir knows my father. We didn't even do a mic test. You guys can hear me in the back? Okay, very good. So I'm really happy to be here and wonderful to get to know you, sir. And happy to have this opportunity, and thanks ICTS for running this such a lovely outreach program. I'd heard a lot about this Kaapi with Curiosity series. And those of you who don't know ICTS, maybe should, I hope you take the time to learn more about this institute. It is one of the premier research institutes in the country, and I have starting with a certain number that we all come across, the number pi. But let me start here. Maybe by the end of this talk, you're kind of sick and tired of mathematics and you want to go and, I don't know, eat something, and you hit some pizzeria nearby, and here are, let's say, there's the two 8-inch pizzas available for a total cost of 300 rupees for a pizza. Oh, by the way, I know that some people from the US are also tuning in. The cost here is in Indian rupees. You know, if anyone asks you $600 for two pizzas, you should never go there. Anyway, okay, so two 8-inch pizzas for 600 bucks or one 12-inch pizza for 675 bucks. Which is the better deal? There are three possibilities. Maybe the two pizzas is better. Maybe this one 12-inch pizza is better, or maybe they're the same. So that's a question. Maybe you can make a note of the numbers or take a shot, and after the program, when you're going to have some tea and coffee, you're going to give me your answer. If you don't get the right answer, you may not be allowed to leave the room. Okay. I will get into what really goes into answering this question. That's really the point, you know, as a puzzle, this is, it's a puzzle, and I don't know, maybe when, I don't even remember at what stage of our lives we come across problems of this type, you know, maybe 7th standard, 8th standard, something like that. A similar problem, suppose you have 100 meters of fencing and you want to make a field and you want to maximize your area. What shape would you pick? Would you pick a square or would you pick a circle? How many of you think it's a circle? And how many of you think it's a square? Fewer hands for square and several hands for circle. Of course, there's no peer pressure. Just because a bunch of you are saying, you know, the truth of the matter is completely independent of what we all might feel about it. Here's a hint. So the dimensions in these pictures are rigged so that they have the same perimeter. And now what do you think? Which one do you think has more area? Okay. That would make the number pi, it will kind of kill certain properties of pi if they were to have the same area. I will get to that in a moment. Alright, so there's a hint. I'm not giving you the answer, you figure it out. And again, we'll talk about this over tea. This is supposed to be a circle, but there's a little distortion. It looks almost like an ellipse to me, and not a circle. So let's get into, what really is a circle. If you want to answer this question and think about what is the mathematics which goes into answering this question, we better be clear about what is a circle. And a point which I will probably harp on many times is mathematics is fundamentally a language. The scientist Galileo famously said that the universe is written in the language of mathematics. The great book of the universe is written in the language of mathematics. So if it were a language, we better be clear about the usage of terms. So by the way, what's a circle? What's a circle? Here's a point. All these points are a given distance away from this point. So what I'm hand waving here, is this a circle? You're almost there, by the way. Yeah.
A sequence of points, when each point in that sequence is at a fixed distance from a particular point.
Yeah. So that was pretty much it. Yes. Yeah, there's a boy there. So, in some sense, you're all correct. You have to just tweak your definitions a little bit. I'll give you so you take a point and you need to work in the plane. So let's say this floor is our plane. I pick a point and I pick a distance. This point will ultimately be called the center of the circle. I pick a distance which will ultimately be called the radius of the circle. And you look at the locus of all points, locus meaning the set of all points from that given distance from this given point. That's the definition of a circle. The set of all points, and it's happening in a plane. It's a 2D thing. Okay, so that's a circle. Here's the circle that O is the center, and the distance of a point on the circumference, that's called the circumference, to the center is called the radius. And if I take 2 times the radius, this pointer might not really work on this. So 2 times this radius, that's the diameter. You take a line segment passing through the center from. Pretty much the first thing we learn about a circle, the first few things we learn is the circumference is 2 pi r and the area is pi r squared. Okay, this is your first introduction to the number pi. Now you got to ask yourself, I've used some more words, circumference and area. So what is circumference? What do I mean by circumference? It's the length of this. And if I want to compute it, what might I do? Here is my circle. I could, for example, cut it, straighten it out, and then you can measure that length. That's by definition the circumference of the circle. What is area? What do you think one would mean by area inside the circle? This is a little more serious. You wanted to answer. Here, I'm giving you a chance now. What do you think we might mean by area? Yeah, and then the question will become how can one compute this? The basic idea with areas is we can compute the area of a rectangle. If I'm given a rectangle, it's length times breadth or width times height. If I can do a rectangle, then I can do any region, and I could do a circle. And the idea, and this is the fundamental idea, one of the fundamental ideas in calculus, is I chop it up into I use vertical lines and chop it up, and then I use horizontal lines and chop it up, and I'll get this tiny little rectangles whose area I can compute. There are some of these rectangles towards the edge which might have a curved part in that it's not quite a rectangle, but it's so tiny that you can pretend it's a rectangle. And this is the basic idea of integral calculus. Yeah.
Then you arrange one like this, and then like this.
Oh, very good. You've seen that. Yeah, beautiful. Yes. Yeah.
And then if you keep on making it infinitesimally small, then it becomes.
Yeah. So you've used a beautiful word, infinitesimally small. That's the key word. Yes. Very good. Excellent. All right. So this is our first introduction to the number pi. Okay. There's some number pi, whatever this number is, and then in school you're given some values for pi to compute. So let's talk a little more about the circle constant. I've already discussed what do we mean by circumference and what do we mean by area. And if you go back to this definition of circumference is 2 pi r, so the circumference divided by, say, the diameter is that number pi. And this is independent of which circle I'm working with. I could take a tiny little circle or I could take a massive circle. Turns out that the circumference by the diameter is a constant. This is a beautiful theorem. And here's a little, for those of you, math trivia. Who do you think first showed that the circumference by diameter is a constant? Okay, good guess. Euler was much too recent. Euler, I will get to Euler. 1730s is when he kind of broke on the scene. Pi goes way before Euler. Archimedes is a good guess. And I also thought this goes back to the Greeks, presumably to Euclid. And apparently this is explicitly stated and proved by in a manuscript from Baghdad in the 9th century. It was somehow known, they were not claiming originality, but they were just putting together what was known at that time. So it's kind of lost in the mists of history. We don't really know who first figured this out. Okay. Yeah. Yes. The very next slide is, yeah, so while I was preparing it, I somehow thought Euclid, but it really goes way back. It goes back to, you're perfectly right, it goes back to the Babylonians and the Egyptians and the Chinese. So I want to show you a famous calculation due to Archimedes. By the way, what is the value of pi? Okay. Okay, all right. So you know such things. So now you're putting me on the spot, but we'll get there. So when you do in a high school, when you compute, you're using numbers like 22 by 7. Does this ring a bell? That's an approximation, and that goes back to Archimedes. Archimedes very well knew that this is an approximation, and I want to show you how he figured that out. Okay. This is what he did. He took a circle of radius 1. Take an integer n, and you consider an inscribed, so I have a circle, something sitting inside the circle, an inscribed regular n-sided polygon. Regular means all sides are equal, all angles are equal, and then let dn be the length of its side. So there are n of these sides in this polygon, and n times dn would be the perimeter of this n-gon, in which case that cn by 2 is an approximation by pi. Let's do this for n equals 6. And let's see what we get. So here's a circle with a regular 6-gon. A 6-gon is a hexagon, a regular hexagon, all sides are equal, inscribed sitting inside the circle, and let me now hand wave a little. So there's a circle of radius 1, so this edge is 1, that edge is 1. Total angle in a circle is 360 degrees. There are 6 equal parts, so each one is 60 degrees. If this and this are equal, then this is an isosceles triangle with this apex angle being 60. Therefore, this is an equilateral triangle. And therefore this is also 1. So each side is length 1, and there are 6 of these. So the perimeter of this regular hexagon is 6. And if the radius is 1, 2 pi would be the circumference of the circle. So this would give me that 2 pi is a little larger than 6. I have extra. This is the shortest part. This is kind of curving around. So 2 pi is little larger than 6, or pi is larger than 3. So this, you get an easy lower bound working with a hexagon. And what Archimedes then did was instead of working with hexagon, then he took the midpoints of each of these segments. And then instead of working with a 6-gon, you divide each one equally into 2 pieces, you get a 12-gon. You get a picture like this. Exercise. Figure out what lower bound pi will be bigger than something. Figure that out. You have to do some easy geometry. Okay. So what lower bound for pi can you deduce from this? Archimedes didn't stop there. So he ultimately, these numbers are, you see that pi is less than 3 1 over 7, and 3 1 over 7 is really 22 by 7. So what he did was he took an n-gon, subdivided it, and to get a regular 2 n-gon, and you have to do a little bit of some geometry like this. If this big edge CE is your n-gon, and then I divide it equally, then if I know this length CE, do a mess around using Pythagoras, nothing more than Pythagoras is needed for this. You can compute the length of this d2n. That's your exercise. And then he didn't stop at subdividing it once. He took a hexagon 6-gon, subdivided it to get a 12-gon, once more 24-gon, once again 48-gon, yet once again 96-gon. Try doing this by hand, and now imagine, Archimedes, this was 2,500, 2,300 years ago. He must have had some non-trivial facility in computing, in coming up with those bounds. Okay. Say this again. He had his students do this? Okay. Yeah, maybe. So this is just for fun. What's a 3-gon called? All right, so far so good. 6-gon, I use the word hexagon. Hexagon. 12-gon, dodecagon. All right, should I go? 24-gon? I should have gotten a bag of chocolates or something. Anyone gets this? All right. I had this slide. I had the most fun in preparing this slide. What's a 24-gon called? It's called an icosahedron tetragon. You might have heard of an icosahedron, an icosa something or the other is a 20 something, and a 20, and then a tetra is 4. So that's how you build that word. Yeah, so the chi can, so I'm no expert on pretty much anything at all, and certainly not on Latin. The chi could be suppressed. It can also be called icosahedron tetragon. A 48-gon. Yeah. So it's like a 40 and an 8. So 40 is a tetra octagon. Yeah, so that's like 4 times 10 and an 8. And that's your hint. Whoever gets the next one, really, I'm something contra hexagon. Yeah. No. Oh yeah. So it's an enya contra hexagon. Okay, so if you like mathematics, you might like this kind of nerdy things of just learning these. Okay, so this is just an aside. This is a famous painting of Archimedes by a French artist, Thomas de George. Archimedes lived in Sicily, that was at that time part of Greece, now it's part of Italy. He was in a coastal town called Syracuse, and the Romans attacked Sicily. A Roman general told these guys, whatever happens, don't touch Archimedes. He is really a treasure of humanity, and you shouldn't, don't kill him. And of course, the Roman brutes, the soldiers, so there's this guy who went and killed him. Legend has it that he was working on a problem at that time, and there are different versions of this legend. Apparently, Archimedes' last words as a soldier killed him were, "I beg of you, do not disturb my circles." And an aspect of this painting which is often pointed out is the Roman soldier's face is in the dark. No one cares about this brute who just murdered some guy. But Archimedes is, light is shining on his face. He showed humanity his unveiled knowledge for us. Okay, here is a brief history of pi, which you like. So it goes back to the Babylonians. So they knew something about pi and also had a reasonable approximation. The Egyptians in the Ahmas papyrus, which still exists, also goes by the name Rind papyrus. Rind was a Scottish somebody who collected art. But Ahmas, apparently in this papyrus, the scribe wrote his name, and it's better to call it the Ahmas papyrus. They had a certain value. The Chinese had figured something about pi, and in school you might also come across this fraction, 355 by 113. I remember having come across this when I was a high school kid. After 22 by 7, if you want a next good approximation, and those of you who know continued fractions, if you know continued fractions, the next convergent is 355 by 113. We had a long Indian contribution. Aryabhatta, Brahmagupta, interestingly and somewhat whimsically, had this square root of 10. Madhava, some other time, I had given a talk on Kerala School of Mathematics in Bangalore. So they had a calculation of pi, something very interesting there in the 14th century in the Kerala School of Mathematics. Here's a maths trivia again. Since when has pi been denoted pi? I had honestly no idea what the answer was. It's a bit surprising, but anyway, anyone has any idea? Yeah, that's the natural guess. So it's not the Greeks. Is almost. Euler popularized it. Apparently, a British William Jones suggested that pi is a good letter for some reason, and Euler used this quite a bit, and is popularized by Euler. Now pi has been computed to trillions of digits. Okay. Now this, yes, very good. And for that reason, it's probably been computed till that point. I want to pause and give you a, say something. Think of me as a researcher, as a mathematician. I'm basically a researcher. And this is basically a curiosity, it's a computational curiosity. If you were to come and tell me, look, I computed the 314 and 13th digit of pi, I might say, okay. If I'm in a good mood, I might even ask you, well, what was the digit? And I can assure you by the time I walk out of the door, I might have even forgotten what that digit was. The point is, in mathematics and in higher sciences, what is relevant is somehow structural properties of pi. And that's what I'm going to get to. I mean, even NASA doesn't need more than 16 digits decimal expansion of pi. So computing trillions of digits is, you can do it as a computational curiosity to test your computational capacity, but it really doesn't have much of a significance either theoretically or for applications. Now imagine you, after it gets dark, go out, stand outside, let's suppose it was not cloudy, and then you stare at the moon and you ask yourself and think about the audacity of sending men to the moon or sending people around the moon, and think of all the delicate calculations that you need to do. Even for those, you don't need anything more than 16 decimals, and even 16 decimals are not required because the way it's 8 decimals by 8 decimals is how it gets stored, so even 16 is not really needed for applications, or for engineering applications, I should say. A lot of this, there's a beautiful book called Pi, a source book by Berggren, Borwein. It's a thick fat book with tons of information on the number pi. But I want to move on to what is interesting mathematically, what is structurally interesting about this number pi, and that will be a kind of point of departure into higher mathematics. So one question to ask is pi rational? So now I'm going to pause for a second, and I have to tell you, I've already told you mathematics is a language. The usage of the word rational here is not in the sense of asking, or saying man is a rational being. Of course, given all the nonsense which is going on, we might argue that man is an irrational being. That is a different story. But we don't use this word in that sense. It's coming from what is a rational number. A rational number is a ratio of two integers, and that's the root is ratio. From ratio comes rational. And it's traditional to use z for the set of all integers, so all numbers of the form a by b, and you can't divide by 0, so b better not be 0. And what's an irrational number? By definition, what's not a rational number? We have to agree on the usage of these words. And well, do I even need to make this definition? If there were no irrational numbers, then why make this definition? So is there an irrational number? Give me an irrational number. Okay, very good. Sorry, I should. Yeah, okay. Yeah, golden ratio. Okay, so we'll. All right, that's a slightly non-trivial statement, and I'll ask you, do you know a proof of it? And you can tell me, we'll talk over coffee after the talk. So there are irrational numbers, some. So, okay, this is the question. So classically, the Pythagoreans So you've learned the Pythagoras theorem that, if I take a right angle triangle, square on the hypotenuse and sum of squares on the other two sides, blah, blah, blah. Pythagoras, it was not clear who exactly was Pythagoras, but there were a bunch of people who, the Pythagoreans. One of them, Hippasus, apparently on a voyage, figured that if you take a unit square, a square with side edge being 1, if this is 1 and this is 1, then the diagonal is going to be square root of 2. And he realized on this voyage that the square root of 2 is an irrational number. And this is a classic, the proof is a classic proof by contradiction. The Pythagoreans were so bothered by this, they threw him aboard. He had to walk the plank. The life of a mathematician is pretty dangerous. Okay, so you might uncover deep insights of the way the universe works, and people might just. Yeah. So in any case, it's a sort of possibly apocryphal. It's a legend anyway. Okay, so square root of 2 is irrational is a fact. There are irrationals. Well, the question then would be, how many do we have? And this, now I should tell you something about an infinite set, or what is infinity. So rational numbers, we start with integers. I can count integers, 1, 2, 3, 4, 5, and so on and so forth. I'm kind of counting. And there is no largest integer. Whatever integer you give me, however large, I can always add 1 and I can get a larger number. So it's an infinite set, but somehow I can count it. Such a set is said to be called countably infinite. And if I work with rational numbers in an integer by an integer, I can arrange my rational numbers, say in a rectangular array, and then I can kind of, in some serpentine way, traverse through all the rationals. So that is also something, it's countably infinite. But the set of irrationals is uncountably infinite. There is no way in which I can count this. And this is a great proof. If you're interested, you should look up a classic called Cantor's diagonal argument. The usual image, and especially relevant since we are in a planetarium, the usual image given for this is, pretend all numbers are like, you kind of, it's like the sky when it's dark, and you look up anywhere, you'll see a lot of stars, and let's say there's no cloud, nothing. So you see a lot of stars. In any direction there might be a star, feels like that, but actually the stars are very sparse, and most of the inky blackness are like the irrationals, and the few stars here and there is like a countable set against an uncountable infinite sky. My brother is here. I don't know if you remember, we used to fight when we were kids at one of the questions before, which is larger, countless or infinity? So this is, I have some childhood memory of having had this argument, which is larger, countless or infinity? And this is a kind of, I got it. This is a kind of meaningless question, but with the definitions of countably infinite and uncountably infinite, we can revisit this discussion. And what you learn in set theory is there is no highest infinity. Give me an infinite set, I can produce a larger infinite set by working with something called the power set. Anyway, I don't really need that. So the point is that there are lots of rationals, but I can still count them. Irrationals, they're much more so. You cannot count them. And it was proved by Johann Heinrich Lambert in 1760s that pi is irrational. And this proof is non-trivial. Okay, so there's no way I can discuss it here. If you're familiar with such words, he used the continued fraction expansion of tangent of x, this trigonometric function that you come across. So this is the first example of something like a structural property of the number pi. All those 22 by 7, 354 by 113, these are at best approximations. Okay, you can get closer and closer to pi via rationals, but it itself is not rational. A somewhat deeper question to ask is pi algebraic? And the meaning of this is there some equation that it satisfies? Now you would have learned this in school. If I have a polynomial ax squared plus bx plus c equals 0, then it has some solutions. Solutions are ax squared plus bx plus c equals 0, minus b plus or minus square root something or the other, b squared minus 4ac divided by 2a. You've learned this. So that's a quadratic, a degree 2 polynomial, and you can write down the roots. The roots of a degree 2 polynomial are therefore algebraic. I'll show you the definition in a second. An algebraic number is a number which satisfies a polynomial equation. Every rational number is algebraic. 5 by 13, for example, is trivially a solution of 13x minus 5 equals 0. irrationals, some irrationals could be algebraic. For example, the square root of 7 would satisfy the equation x squared minus 7, square root of 2 satisfies x squared minus 2, x squared minus 2 is a polynomial. How do I know there isn't a 57-degree polynomial that pi satisfies? You can ask the question, and this is a deep question now. And I'm headed towards that question. So towards that, let Q bar denote the set of all algebraic numbers, all possible solutions of all possible polynomials you can cook up. And what is transcendental? Again, a technical word. A number is transcendental if it's not algebraic. It doesn't mean, oh, you have a transcendental experience. It's just a number, okay? It doesn't satisfy a polynomial. That's all it means. So Q bar, all algebraic numbers is also countable. Rationals is countable. If I take a degree 1 polynomial ax plus b, I just need 2 rationals. If I take a degree 2 polynomial ax squared plus bx plus c, I just need 3 rationals. I just need a handful of rationals, finitely many rationals for any polynomial. Because I'm building up with some finiteness in this discussion, I still stay within the framework of countably infinite. It's a relatively easy exercise. And if I have a degree 2 polynomial x squared plus bx plus c equals 0, there are only 2 solutions, minus b plus or minus square root b squared, whatever it was. So there are 2 solutions. If I have a degree 3 polynomial, I will have at most 3 solutions. Degree 10 polynomial, at most 10 solutions. Again, there's a finiteness built into this discussion. In other words, if I look at all solutions of all possible polynomials, it's still somehow countably infinite. In particular, there are lots of transcendental numbers. There are uncountably many transcendental numbers. Again, the image of the sky, the stars being now algebraic numbers, and everything else being uncountably infinite. Yes? Infinite degree yeah, so now here I need finite degree. There is an interesting construction, it's called a power series. I can look at infinite degree polynomials, and that leads to certain kinds of thinking. But here we are working with finite degree. By definition, a polynomial has some finite degree. So Ferdinand von Lindemann in 1880s proved that pi is transcendental. So there is no polynomial you can possibly cook up which pi is going to satisfy. And the proof, this is now serious. This is not even undergraduate level mathematics. This is typically at graduate level algebra that you learn this kind of stuff. What Lindemann did was he showed that E, an exponential of an algebraic number, is transcendental. That was his theorem. Exponential of an algebraic number is transcendental. But then there is this famous Euler's identity that e to the I pi, the square root of minus 1 is also denoted I usually, e to the I pi plus 1 is 0. So if pi is algebraic, square root of minus 1 is algebraic. It satisfies the polynomial x squared plus 1 is 0. Algebraic and algebraic is also algebraic. E to the algebraic would be transcendental by the theorem, but then e to the I pi is minus 1. Minus 1 is, it's an integer, it's algebraic. So that contradiction will say that pi could not be algebraic, therefore transcendental. And the beauty is it uses this equation, which is often considered one of, if not one of the most beautiful equation in mathematics, because it involves 0, it involves 1, you can build up all numbers from 0 and 1, it involves the fundamental arithmetic operations of addition, the operation of multiplication, it involves pi, it involves the number e, which is fundamental to calculus, it involves the square root of minus 1 that you need to cook up complex numbers, and finally it involves this notion of equality. When are two numbers equal? And the notion of equality, when are two things equal, you might think is brewing heavy weather on something which, okay, two numbers are equal, what's there to it? Towards the end, I'll show you an example where two numbers which are obviously and blatantly distinct looking, but somehow almost feel equal. So this is something serious. Nevertheless, it involves all the basic ingredients of mathematics, this equation, which is why people consider this one of the most beautiful equations in mathematics. And this was used in Lindemann's proof that pi is transcendental. Yeah. Yes, it could be. But on the other hand, by definition, it's a real number since it's a circumference which is a real number of a circle, divided by the diameter, which is also a real number, and the ratio of two real numbers is real. So one knows pi is real. I want to show you for good measure Ramanujan's formula for pi, or 1 over pi, and you people have heard Ramanujan's name? Okay, he arguably one of the greatest mathematicians that India has produced, and you might know that somehow everything that Ramanujan did was like a tip of an iceberg, and there was something always behind that, and what the little that you saw was just mind-boggling. I mean, you don't need to be a mathematician to see that, you just take a few steps back, and you got to ask yourself, how did he cook up something like this? Okay, I'm not even going to try to read it, but okay, there's a certain expression, there's an infinite sum running over all non-negative integers, and each summand is some terrible looking expression in terms of n, and miraculously this whole thing captures 1 over pi. This formula is so amazing. It's first of all rapidly converging. It's rapidly converging meaning it's easy to compute because I have all these factorials, but the size of the factorials upstairs and downstairs are essentially the same. Just 396 to the 4n, there's an exponential term sitting in the denominator. So the ratio is very small. So each term goes to 0 very quickly, and the series converges rapidly. That's what one say. But what is miraculous is if you take just the first term for n equals 0, put n equals 0, 4n factorial becomes, for n equals 0, very good, 4 times 0 is 0 and 0 factorial is 1. So that becomes 1. N factorial is also by the same token it's 1. 1 to the 4 is 1. 396 to the 4n becomes 396 to the 0. Anything to the 0 is 1. That's disappeared. That expression there on top, something times n is gone, and 1103 remains. The square root of 8 is also 2 root 2. So 2 root 2 times that is 2206 times root 2 divided by 9801. Flip it up, take the reciprocal. So pi is, this expression is already amazingly accurate. Just this is one tiny example of this guy's genius. It's just impossible to fathom how he cooks up these things, how he cooked up these things. And each additional term gives 8 decimal places, and people use this formula of Ramanujan to compute pi to lots of decimal places. Just a curiosity, okay, but it's. So what I've done so far is I've introduced the number pi, which you have seen in school sometime, and talked a little about structural properties. It's irrational, it doesn't satisfy any polynomial equation, and there are all these beautiful or bizarre formulae for pi. Yeah, sure, anytime. Yeah, so there is some, of course, with everything with Ramanujan, there is something going on. So there is some hypergeometric series that he was working with, and I will say something, I might just mumble something, yeah. But he certainly had some theory behind this. Okay, this formula has been used to compute pi to great precision. And now I want to slightly change tacks. Okay, hopefully I've introduced the number pi and you have learned one or two things. Okay, before that, just to advertise a little, some years ago I used to work at IISER Pune, and 2012 was the 125th anniversary of Ramanujan, was also the National Year for Mathematics. We made a documentary on Ramanujan. It's there on YouTube. It's called The Genius of Srinivas Ramanujan. If you haven't watched it, go watch it. It's the point of this documentary was try to understand what makes a genius, why is Ramanujan a genius. Even after the end of the documentary, it's not as if one has an answer to this question, but you have a greater appreciation for who the man was and what he did. Okay, so now I'm going to change tacks. I'm going to ask you, what's a lemniscate? You know this. So what's a lemniscate? So you answer, what's a lemniscate? Yeah, some polar something is going to happen in a moment. But hand wave, is this a lemniscate? So a lemniscate, lemniscate is that any infinity shaped curve is called a lemniscate. A lemniscate is a figure 8 or an infinity shaped curve. In Latin, lemniscatus means decorated with ribbons. In Greek, lemniskos means ribbon, apparently. Yeah, honestly, I don't understand these things. It's all Greek and Latin to me. But that's what it is. Okay, a lemniscate is an infinity shaped figure. This particular lemniscate is given by this equation: x squared plus y squared the whole squared is x squared minus y squared. Okay, some equation. I want to take this lemniscate and do pretty much whatever we have done so far with a circle and see what you get. So I want to compute how long is this. I want to compute the circumference, the length of this curve. Now it's clear from the picture or from the equation, if I replace say x by minus x, this equation is unchanged. So there's some symmetry to this. So if I want to compute the total length, it suffices to compute one leaf and then take 2 times that. All right, I want to compute the length of one leaf. Now I can do the same, I can cut it and kind of pull it, and that's the length. This is just to naively to explain what we mean by length. I really want to compute this. Okay, what is that number? Now we get into somewhat deeper waters. So I want to compute the circumference of this lemniscate. I'm going to denote that by this symbol. I don't know how many of you have come across this symbol. There's a mathematician, this question is not for you. So this is also pi. It is a calligraphic pi. If we use a certain software that we use to type mathematics called LaTeX, what you use is var pi. So I'm going to call this var pi, okay, like a variable pi. It's a calligraphic pi. So I'm going to denote var pi to be the circumference of one leaf of the lemniscate. And I want to compute that number. Let's see what it is. And so the total, by symmetry, the total circumference then is 2 times var pi. So for this, I need to give you a crash course, a 1-minute crash course in computing lengths. Suppose I have some curve given by some equation, y is equal to a function of x from somewhere to somewhere, from x equals a to x equals b. I have some curve, some graph of some curve, and those of you who have done up to 12th standard mathematics, you would have seen all of this. So I take a graph between 2 points, x equals a to x equals b, and I want to see how long is this, and I want some solid means of computing this. And the idea, the basic idea of calculus, this word infinitesimal that you use is to, I want to solve a problem, you chop it up into tiny little problems, solve your tiny little problem, and then you add it all up. So I have a curve, maybe it's very, very curved, but if I take a tiny step on the curve, it will pretend to be a straight line. So I take a tiny step along the curve, but any step in some direction can be afforded by taking a tiny step along the x-axis and a tiny step along the y-axis. So how can I compute? So let ds represent a tiny step along the curve, and then Pythagoras theorem applied to a tiny little triangle with ds as the hypotenuse gives me an equation like that. That ds squared is dx squared plus dy squared. A tiny step along the curve is ds. The square on the hypotenuse is the sum of the squares on the other two sides. Pythagoras. Well, it's just then messing around with this. I can just take some formulae, I take square root, I get ds is some expression, I pull out the dx squared all outside the square root sign, and that becomes a dx, and what remains inside I can package it as 1 plus the square of the derivative. Dy by dx is called the derivative, the slope of the tangent of a curve you had learned in calculus. So this is some expression for a tiny step along the curve, and then you add it all up, and the process of adding up, summation, is what's called integral. So this integral sign is supposed to be a distorted s, and I'm adding up all the tiny little steps along the curve. So I have some expression like this. Now if I want to pull this calculation with this equation, you would have learned things like implicit differentiation. I know this might ring a bell if from your 11th, 12th standard mathematics. You could do some implicit differentiation there and get an expression for the derivative. It's some terrible expression, then I'm going to square it and square root, it's a total mess. Okay, so you just need some other way to think about this. So sometimes it's better to kind of reorganize your thoughts and work with what are called polar coordinates. This is what do I need to know a point? So let's say we are on the plane. If I know how much horizontal distance I got to traverse and how much vertical distance, that's the x and y coordinates. Two numbers will determine a point. If I'm in 3 space and I fix my origin in that corner and my x, y and z axis are like this, I need 3 numbers to know a point in 3 space. Let's work in the plane. These same 2 numbers, I can think of it in a completely different way. I can take a radial line kind of like in a lighthouse, kind of going all around and see where it hits the point, and then what is the distance from the origin. So this distance from the origin of a point, I'll call that r, suggesting radius, radial distance, and the angle that it's got to sweep before I hit that point, I'm going to call that theta. So these 2 numbers, r and theta, serve the same purpose. And then if you remember your basic trigonometry, I got a right angle triangle there, hypotenuse is r, angle theta, y then would be r sine theta, and then the x would be basically the adjacent with respect to theta, and by definition of cosine it would be r cosine theta. So x and y can be retrieved as r cosine or r cos theta, as you might say, and r sine theta. And then if you plug in those expressions into this, you know that sine squared plus cosine squared is 1. That's also Pythagoras. This guy becomes r squared, that's r to the 4, and this becomes r squared times cosine squared minus sine squared. Cosine squared theta minus sine squared theta, one of your basic double angle formulae that you learn, I don't know when, 10th standard, 11th standard, says that it's cosine 2 theta. And this equation is far simpler looking than that previous equation involving x and y. So you could use this r square equals cosine 2 theta and set up an integral to compute the arc length, and you will get an integral of this type. Okay, so you can skip. So there is a certain integral which captures my number which I wanted to compute, the length of one leaf of a lemniscate. And now all you high school students, note down this integral. I challenge you to solve this integral. You learned all these substitutions. If I see this expression, try this. If I see that expression, try that. Go try. The problem is, this is, yeah. You can do that. You can do that if you know, and you will get some series. Yeah, you will get some series. Excellent. If you know such thing, awesome. Yeah, you could do that. So you will get some expression for pi, var pi, and then the question will become, okay, how do can I say something more about the sum of that series? So expanding in terms of a power series, this is just answering his question, is somehow not considered an elementary means. My challenge was to use, what we learn. In any case, nothing stops you in computing this approximately and you get some number. Okay, 2.622, whatever it is. This lemniscate constant, to appreciate this, let me put it against the number pi that we have been talking about. So the circle constant, which I'll call is the number pi, I'm going to call it the circle constant, and put it against the lemniscate constant. So pi is given by this kind of integral. If you're familiar with integrals, you can make some substitution, put t is something, I don't know, sine theta or something, and then denominator becomes cosine theta, dt becomes cosine theta, d theta, cancel the cosine, integral of d theta is theta, and the limits now would be minus pi by 2 to pi by 2, blah, 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 you get pi, okay, fine. So just take that as a blackboard. I have an expression involving an integral for pi. I have some expression involving the integral for var pi. Even if you know nothing about integral calculus, just look at this as some work of art, and I can ask you, spot the differences. Okay, it looks identical. Is it identical? It can't be identical. They're somehow different number. Maybe they're the same number. I don't know. But is it identical? There is one difference. The t squared is a t to the 4. That is suggesting that there's something very similar going on. It's suggesting, is pi related to var pi? Is the circle constant related to the lemniscate constant? Do you think 13 billion years ago, when the universe was forming, on a dark tempestuous night, or maybe it was always night time then, I don't know, when it was dark and tempestuous, the number pi and the number var pi, these two little girls got separated. Will they ever find themselves again? You got to drink some strong coffee and write a storyline there. Okay, so in any case, there is this question. Okay, so are these two related? One can ask a better question, a meta question. For every fact that we know, and I already threw a bunch of facts at you for this usual pi, is there an analogous theorem, an analogous fact for var pi? This is a serious, it gives you an entire fund of research level questions. And to give you an example, two mathematicians, Bruce Burnt at the University of Illinois at Urbana-Champaign and Bhargava, who was at Mysore, asked themselves the same question, and that wild formula of Ramanujan, they asked themselves, is there an analogous formula for var pi? And using whatever was the theory of hypergeometric series I was mumbling, they discuss such things and they prove a similar formula for 1 over var pi. So go to that Berggren, Borwein and Borwein's book, pick a fact about pi that you like and see if you can prove something similar about var pi. So there's something interesting going on. And this question of whether these two numbers are related fascinated lots of great mathematicians. And I want to show you what one great mathematician, Gauss, one of the greatest of all times, what he did when he thought about this question. So towards that, I need a little bit of, there is a typo there. I need a little bit of something called the arithmetic geometric mean. And this is a beautiful construction that, with high school mathematics, I can motivate this. Take two numbers, okay, A and B, real, positive numbers. And you learn these things. Arithmetic mean is also kind of colloquially called average, is A plus B by 2. And the geometric mean is square root of AB. What is the first thing that you learn about these things? After. Very good. Excellent. So that if you don't know proof, that's an exercise. Prove that the arithmetic mean is bigger or equal to geometric mean. This is relatively easy. You take the 2 across. 2 square root of AB, I want to show is less than or equal to A plus B. Move it across. I want to show that A minus 2 square root AB plus B is bigger than or equal to 0. And that becomes the square of square root A minus square root B, the whole square is bigger than or equal to 0. And most inequalities in mathematics hinge on this idea that the square of a number is positive or at worst is 0. All right. So now what I do is I'm going to hand wave through something. I got two numbers, A and B. I take their average, A plus B by 2. I take their geometric mean. Okay, for me this is on the left, for you it will be the other way around. Okay, so make that switch. So I take two numbers, A and B, take their arithmetic mean, take the geometric mean. Now I have these two numbers, take their arithmetic mean and geometric mean. I get two new numbers. Take their arithmetic mean and geometric mean and keep going. Okay, the question is what do you end up with? Are you with me? I have two numbers, take their arithmetic and geometric mean. I have these two numbers, take their arithmetic mean and geometric mean, or this pair of numbers, take the arithmetic mean and geometric mean. I'm essentially hand waving. The exercise coming your way that, okay, I will end up with these geometric means, and the geometric means being less than or equal to arithmetic means. The geometric means are increasing, but not arbitrarily. They're all bounded above by the arithmetic mean. So these numbers are increasing, but they're kind of increasing and kind of tapering off. They will hit a limit. These guys are decreasing, but they're not arbitrarily decreasing. They're going to come to some limit. And the beauty is these B's, the geometric means and these arithmetic means will hit a common, they'll get closer and closer to some one number. That's an exercise. Prove it. If you are familiar with proofs in calculus, epsilon delta proofs, this is a serious exercise. So show that the limit of this geometric means and limit this common limit is called the arithmetic geometric mean of those original two numbers. Okay, so here's a definition which needs nothing more than a bit of calculus and idea of limits and basic constructions that you see in school. Gauss, this great mathematician, proved this amazing fact that the arithmetic geometric mean and 1 and the square root of 2 somehow relates these two, the circle constant and the lemniscate constant. Boom. So Gauss, he maintained his Tages book. Tages book means daily. Tag is day and book is book. Tages book is just like a daily book, a diary. He used to maintain a diary, and he sort of waxes eloquent about his proof that the arithmetic geometric mean of 1 and the square root of 2 happen to be the ratio of the circle constant to the lemniscate constant. And he cleverly uses a certain integral involving the two inputs A and B and an integral square root a squared cosine squared theta plus b squared sine squared theta. If I did 1 and the square root of 2, I'm going to be looking at square root of cosine squared plus 2 sine squared theta. And he cleverly made a substitution. If I have a and b, his clever substitution said that this same integral will work for a1 and b1, the first arithmetic and geometric mean. By the same process, you'll get for a2 and b2, and in the limit, I'm going to see this. And then one needs to do extra work, and this is a serious theorem. Okay, I cannot explain the proof, but this is Gauss's genius that he was able to see this. This is Carl Friedrich Gauss, one of the greatest mathematicians. Here is a famous quote: "Die Mathematik ist die Königin der Wissenschaften und die Zahlentheorie ist die Königin der Mathematik." Can you guess the meaning? Die Mathematik. Die is the German definite article. It depends on the gender of the noun. Mathematics is feminine, so it's die Mathematik. Mathematics ist is die Königin. Königin. Queen. Queen. King is Kaiser. The mathematics is the queen. I just told you it's feminine. Mathematics. Mathematics is the queen of the Wissenschaften. Sciences. In a previous talk, when I asked this, one student guessed that, is it witchcraft? And I thought, wow, that's awesome. So mathematics is the queen of the sciences, and the Zahlentheorie, the German word for number is Zahlen. Zahlentheorie is the queen of mathematics. Beautiful. Mathematics is the queen of the sciences, and number theory is the queen of mathematics. Every number theorist, I'm a number theorist, every number theorist kind of loves this quote, and so do I. Okay, so now let me just throw analogous to the number pi, where pi is transcendental, and these are deep theorems. This was proved by another great German mathematician, Carl Ludwig Siegel, in the 30s. I'm not going to pretend I understand a proof, but Siegel's proof, and in particular it's irrational, Siegel's proof then morphed into an entire theory which has now become a subject by itself called transcendental number theory. And let me show you another aspect of pi and var pi. The Basel problem was this problem. There's an infinite series. Consider this series. Now you have to understand something. When you learn basic arithmetic, go back to your first standard or second standard or whenever we learned how to add numbers. 1 plus 1 is 2 and 1 plus 5 is 6 and so on and so forth. You add two numbers at a time. It's a binary operation. The input is two numbers and output is one number. Now I'm adding infinitely many numbers. So you've got to ask yourself, well, what does it even mean? And then this is where calculus comes to the rescue, and there's some limiting process. And the idea is that converges means it doesn't it's all positive terms. I have a priori no guarantee that it's kind of shooting off, getting arbitrarily large. Fact, it converges. It adds up to something finite. And if you know some calculus, the quickest test is to compare it with the integral of 1 over x squared, and you might know integral of 1 over x squared is minus 1 over x, and then this is like, fine. It's something finite. There's also a simpler proof. 1 over n squared can be compared to 1 over n times n plus 1. In size they are the same, and 1 over n times n plus 1, I can split it up as a difference of 1 over n minus 1 over n plus 1, and then it starts telescoping. If you understand such words, fine. Otherwise, just take it as a fact, okay, it's something finite. And then it was a famous open problem asked by an Italian mathematician, what really is the sum of this series? And great mathematicians thought about this. Leibniz thought about this. This was an unsolved problem for more than 100 years or almost 100 years in the history of mathematics. It became famous as the Basel problem because many people from the Bernoulli family tried to solve this problem. And until a 25-year-old kid came along, his name was Euler, and he proved that this sum is pi squared by 6. This is, honestly, it makes a good case to be in anyone's top 10 list in great theorems in mathematics. Certainly makes it into my top 10 list. And the beauty is, okay, I got these numbers, these 1, 2, 3, 4, etc. I square, I take reciprocals, I add. What has that got to do with the number pi? Where did pi suddenly come in? So such are the questions to ask. There is Euler. Euler was one of the great mathematicians, one of the greatest, the most prolific mathematicians of all time. He went blind towards the latter part of his life, and he the last few years, even after he went blind, it didn't stop how prolific he was in producing mathematics. Legend has it that he could come up with a theorem between 2 successive calls for dinner. Okay, so it's a legend, but he was certainly extremely prolific. Here is a kind of cute question. I give you 2 numbers at random. From this pocket, I take out a number. From this pocket, I take out a number. I throw it at you. And I ask you, what are the chances that it's relatively prime? So you need to know the meaning of relatively prime. 15 and 21 are the relatively prime. 15 is 3 times 5. 21 is 3 times 7. So I have the same 3 sitting somehow in both of them. So 3 is the common divisor. Relatively prime is when they have no common divisors. So given 2 integers arbitrarily at random, what are the chances they're relatively prime? Answer, 6 by pi squared. This is serious, but clearly there's got something to do with that. So, a series like that has this, and proving this needs certain insights of Euler. Anyway, all right, I wanted to show you this series, and now one has to compare the series with a slightly rewritten Euler. Instead of adding from 1, 2, 3, I work through all integers, and since I'm reciprocals, I don't want the denominator to be 0. Then it would be pi squared by 3, where pi is that expression which I've already thrown at you. Similar to this formula is another beautiful formula of Hurwitz from the 1890s, that if instead of working over 1 over n, I work over integer plus I times an integer, and for good measure I take the 4th power, take the reciprocal, add it all up. Compare the formal similarity of this left hand sides, and right hand side there I had pi, and here I have var pi, whose integral expressions look so similar. And so now there's got to be something going on. Why? One is, why are these formulae true? That is one. But why are these formulae so similar to each other? How does one think about it structurally? And this, so pi, var pi and pi somehow play a similar role. What is going on behind this? And then there's a plethora of this kind of formulae which came out through the last century. And this then gets into modern, very serious mathematics. There's a conjecture due to Deligne from the 70s. Euler's formula and Hurwitz formula are special cases, prototypical examples of an entire area of research in number theory called special values of L functions. I work in that area, and this is governed by this conjecture of Deligne. There is Deligne. He is one of the legendary figures, one of the greatest mathematicians of our times. He is one of the few mathematicians who was awarded a Fields Medal as well as an Abel Prize. I want to draw your attention to a certain magazine here, and we are lucky to have Arvinda in this audience, who is an editor, who is the editor of this magazine. This comes out of Bangalore. The October 2025 issue of this magazine has an interview of Deligne. I urge you to take the time to read this interview. You will get a feel for why this person is just so fantastic, why he is such a legend. He works at the Institute for Advanced Study at Princeton. That's Deligne, by the way, on the bicycle. He's always on his bicycle. So I conducted the interview in this article. This is a great place in the world, and certainly in the world of mathematics and physics. These windows here, the person who occupied this office from 1930s to 1950s, his name was Albert Einstein. Symmetrically on the other side, which you don't see here in that office, was Oppenheimer. If you have watched this movie Oppenheimer, about the Manhattan Project, Oppenheimer was the director of this institute. I had an opportunity to spend some months at this institute on my previous sabbatical, and during that time I spoke with Deligne quite a bit, and a highlight of my career is a certain paper that we wrote. What I want you to just look at, I want you to look at just one word. There's this word motives. Motives, again, is a very serious word. It's got nothing to do with motivation. It comes from the French word motif, from art. But I want you to look at the word periods. The word periods, what you first come, sine x is a periodic function. If I take an angle and I add, go on full circle, it doesn't change the value of sine. So in radians, sine x plus 2 pi is sine x. So 2 pi is a period of a trigonometric function. There's a periodicity. It repeats. It's such a word that we are using. And this word periods is a serious word in mathematics. I realize that I've run out of time, so I'm going to slightly hurry up. I have run out of time, right? Yeah. So I'm going to wrap up soon. So let me just tell you that the word periods and the number pi and the number var pi are all examples of periods. So what is a period? There's Don Zagier, one of this kind of number theoretic geniuses at the Max Planck Institute, and Kontsevich was a student. Kontsevich is also a Fields medalist. They came up with a certain definition, a purely abstract definition, as any number which is the value of an integral, where the integral has a rational function and what I'm integrating is also cut out by rational functions. As an example, the number pi, there are several different integrals. This is a polynomial 1 plus t squared. 1 over a polynomial is an example of a rational function, and I'm integrating over the entire line. This is just dx dy is the area of a tiny little rectangle which I've added up over this entire circle. This is literally the area of a circle of radius 1. So that's the number pi. So the number pi is a period. Similarly, var pi is a period, and that's very serious already. It needs the theory of elliptic curves. It's a big area in arithmetic geometry. So let's denote by P the set of all periods, and now one wants to understand what is the set. What kind of numbers live there? Pi lives there, var pi lives there. What else? There's a reference to Kontsevich. And there are famous conjectures. You'll become famous if you solve any of these. It's a famous open problem that 1 over pi is not a period. Pi is the value of a beautiful integral, but 1 over pi, even though you have this Ramanujan like wild formulae, 1 over pi, no one seems to know whether it's the value of any interesting integral. The number e that you come across when you learn basics of exponentials and logarithms, that's the definition of e. No one seems to know whether the number e is the value of an integral with rational integrand and integrated over space cut out by rational functions. So I'm essentially, this is my penultimate slide. Summarizing, we looked at these two numbers, pi and var pi. One of these, pi, is there everywhere. It's helped us to understand circles, planes, sound, light. Sin x is a wave. If I have two waves and these waves start mixing, there's an entire theory called Fourier analysis which tells you how to study that. You can't start on any of those without the number pi. Likewise, without the number var pi and similar numbers, these are needed. Basic ingredients to study elliptic curves, which feeds into cryptography. You go out, you're going to answer the pizza problem, by the way, and then when you figure out which is the better deal, and you use your cell phone to make a payment, a UPI payment, you are using serious mathematics of this type. Okay, so cryptography feeds into internet commerce. Ultimately, both are just lengths of curves. That's the beauty of it. Go back and meditate over. We started there and see. Look at the evolution of knowledge. So I want you to go back asking yourselves, what is your favorite number in mathematics? Okay, you don't have to tell me. Okay, maybe you can tell me if you want. What is your favorite number? And give it a little complexity. Don't say, I like the number 4. Okay, that's too simple. Make it like pi or something. And then you've got to ask yourself the question, is it a period? You may not be able to computationally answer this. You have to think of this structurally. What do I mean? So here's the beautiful example. There are such numbers. Pi times square root 163 by 3 is some, and that agrees with this logarithm of an integer up to so many decimal places. Even more so, there are numbers which have completely different origins which agree to 80 decimal places. There's a lovely papers by Daniel Shanks giving you examples of such numbers. So you may not be able to computationally address this question. You have to think theoretically and structurally. Okay, so what's your favorite number and is it a period? Well, thank you very much for your attention.
Thank you, Professor Raghuram. We'll quickly take a few questions from the audience. please raise your hands. We'll come there and all, make sure that you speak to the mic. Yeah, who'll take the first question?
There.
Yeah.
Thank you, sir. Nice talk. You said that pi comes in various areas, even in physics and maths. There are series that are already discovered, or they are still yet discovered. As I heard last year, some new series were discovered by some string theorists and all.
Sure.
So, are these, all of these series, do they have any underlying symmetry? As a number theorist, do you believe that they might be connected intrinsically?
So that's I told you Deline's conjecture. Of course, I can't state what the conjecture is. It just needs too much machinery to state it. But there are good reasons to expect formulae of that type, and more so. Yeah. So the number pi shows up. If you have had some complex analysis, you will see 2 pi I coming in lots of places. But there are good reasons why those formulae hold.
Nice presentation, Raghuram ji. Got to learn lots of things. But as you said, the fundamental thing that pi is the circle constant, right? So whatever equations and proofs is involving pi, can I relate it back to somewhere circle? Everything?
Yeah. So this is a legitimate question, and depending upon the particular example at hand. For example, you can take Euler's formula, the 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, etc., added up to pi squared by 6. Show me a proof involving a circle. I don't know. So one can ask this question, it's a legitimate, it is not clear on the face of it. It could be done, it could be pulled off, I would like to imagine with some examples. Although right now I'm kind of furiously trying to think in my head. I don't have an example to offer at this moment, but the question makes sense. Take a fact about pi, show me something with a circle. Yeah. Excellent.
Think of the inverse square law for the inverse square law for the intensity of light. So you can think of
somebody told me. Yeah, go on, keep going.
I mean, it's a very popular video on YouTube. So basically you can think of it as you sum over, like it's circles, I guess, because you know what the intensity of of a light wave it's as a fraction of the area volume area of the thing. So you add up successive you add up, like you imagine placing light sources on the real line, and you add up the light source, and somehow I forget the exact proof, but there is
somebody told me apparently there are some YouTube things where this is so what he's trying to suggest, Drupad, right? So what Drupad is trying to suggest is there is a beautiful physics-based proof of Euler's theorem involving intensity of light, imagining lots of light sources placed along a line and asking yourself what is the total intensity or something, and in that calculation you will see pi. So there is a way to organize one's thoughts with Euler's theorem involving where actually a circle is physically playing a role. So that's one example. Depends on which example we are working with, which fact of pi we are working with. Very good, thank you.
Hello, sir. Yeah, Aniket. Thank you for the presentation. It was very helpful. I have a slightly off-beat question. I have a daughter who is 6 years old. How can I make math fun for her?
A fundamental aspect of mathematics is beauty, and somehow when we go through our mathematical education in school, if you ask a generic school kid which subject are you most scared of, chances are mathematics is the answer. Chances. That's unfortunate. Probably also because of the way we go through mathematics, it's kind of a lot of drills, and drills meaning just keep doing same kind of problem again and again. How to inculcate a feeling of wanting to like it, I don't know. So somehow someone has to expose your daughter or somebody to the idea that there's something truly joyful about learning certain mathematical proofs, statements, the same at that level, elementary, arithmetic, how to kind of, there are fun problem books that one can try. There are no easy answers. What you're asking is a big question in pedagogy. How do you make mathematics interesting? This question gets asked when I was at ICER and even elsewhere. How do you increase the number of students getting into mathematics? One may ask this question. There are no easy answers. But one idea which is missing in school time education is the idea of beauty. I can tell you most number theorists, for example, pursue number theory not because it has all these applications to cryptography and internet commerce. It has, that's fine, but it's fundamentally beautiful. That's pretty much why. There's no difference between, say, a number theorist and say a painter or a musician. It's more art in that sense, and that spirit has to come out at school time education. Yeah.
Thank you.
It's a really basic question.
Yeah.
Okay, it's a really basic question, but why was it named Greek letter pi though? Like there's alpha, there's beta, there's gamma, delta.
So some that British guy pi, and sure, there's alpha, beta, gamma, and they can go all the way to omega, the last letter in the Greek alphabet. So pi somehow stuck.
Yeah.
Yeah.
Yeah, just one thing. I mean, what if pi was 3? Would that have changed physics and maths? Not 22/7 or something like that.
We might not have evolved those 13 billion years ago. I told you on a dark, tempestuous night, the whole world would be different if pi. You see, this nature forces pi to be what it is. It is not up to us to change it to 3.
What if?
So what if pi was 3? The idea, we might be completely, if we even existed, we might be just, who knows what. Yeah. This is the kind of thing, you have to stay up through the night, and then, that's when somehow your mind is attuned to wondering about this kind of questions. So I have nothing to offer. I don't know, what if, sure.
Thank you for the talk.
Yeah, you're welcome.
So pleasant afternoon. Everything keeps changing in the universe. In terms of time, it is 13.8 billion years, and in terms of space, it is 93 billion years.
Okay.
93 billion light years.
If you say so, I don't know.
Will they, both are same.
Fine.
In terms of time, it is 13.8 billion years.
Yeah.
In terms of space, it is 93 billion light years.
Okay.
Will there be a hypothetical situation when the value of constant discovered by man, the value will also change?
It's similar to, it's highly unlikely. These constants, these are universal constants. They are not going to be changing somehow. So the ratio of your circumference to a diameter is going to be the same constant. You are asking if the notion of distance itself changes. I don't know. So physicists wonder more about such questions. My answer is the value of pi is not going to be changing. So here we have an interesting answer coming. Yeah.
So in non-Euclidean geometries, we define a circle as the locus of all points with some distance.
Yes.
So in a non-Euclidean geometry, we'll have a different notion of distance. So it was inspired by these questions actually. Yeah. So we'll have a different notion of distance in some geometry, yes. And then the locus of all points, a given distance in some random geometry, that would yield. How do you even make the calculation of pi? Like, what do you do?
Yeah, I don't know. Yeah, so.
How do you even define a circle? There's a definition.
I will. This is a fantastic question. I'll for the audience, let me transcribe the question. Take a sphere. Okay, before we go to a sphere, what's a triangle? I have 3 sides. And you learn in high school, that the sum of three angles of a triangle is 180 degrees. Now, let's work on a sphere. So I take 3 points, I take the North Pole, say here's my equator, I take 2 points on the equator, I join from the North Pole to a point on the equator, from the North Pole go to a different point on the equator. This, when it touches the equator, I have a 90 degree there, I have a 90 degree here, 90 plus 90 and some angle between these. So the sum of three angles of a spherical triangle is more than 180. So this, if you haven't seen this, this is where the game starts. So when your notion of distance has changed, it's not the shortest path as a crow flies, but somehow as a flight going from there to, I didn't say that right. Anyway, so suppose I take it on the sphere. When the notion of distance has changed, then if I go back to these definitions of circle and whatever I was talking about, will the number pi be something different? You're a different student. I don't know. I don't. The floor is. I don't have a good answer.
I have a question.
Yeah, there's a question here. Yeah.
Thank you for the talk and thank you for shedding light on the lemniscate constant. So my question is that apart from circles, is there any place in nature where pi appears? Like just to make it more joyful to learn mathematics, like understanding the beauty of pi.
Is there anywhere in nature that pi appears?
Yeah.
Take a wave. If you want to do anything, try to do any calculation with a wave, it's unlikely that you'll be avoiding pi. Because a wave, the fundamental curve which gives you a wave is a sine function or the cosine function. And pi is somehow intrinsic to such a function. And so in physics, and for example, if you take a pendulum and let it oscillate and you want to do some calculation, figure out some problem with this simple harmonic motion, you will need the number pi. Yeah, maybe I'm pretty sure, honestly, I've forgotten basic physics and such kind of physics, but with pendulums, you should be able to come up with lots of interesting examples where pi is playing a serious role.
Okay, thank you.
Yeah, pendulums. I think I will go there. Go to your favorite book in physics and pull out something on pendulums. Yeah. Yeah, sure. There was also one. Wait.
Yeah, so thanks Raghu for this very interesting talk. And I happen to be his batchmate. And he was JE2 in our batch.
Yeah, come on. Yeah, I was. Okay, fine.
We make a little deal about it. And he wanted to join maths, but everyone was after him to join CS. But eventually he went back to the math. So maybe you can tell us a little bit about your evolution from after CS. Where did you?
Yeah, so Deepak and I go back a long time from our very first day in IIT Kanpur. So I happened to get a pretty good rank in this entrance exam for IITs, and top rankers took computer science. So I, in Hindi जैसे बोलते हैं बहती गंगा में हम भी बह गए, सब लोग computer science ले रहे हैं, I also took computer science. Okay, but that somehow I think the calling of mathematics was always serious, and pretty quickly I realized that I do want to pursue mathematics. One of my professors, I hope she is online, Professor Shobha Madan, she helped me kind of expose me to the right sort of books to look at and what to study, and then I went to Tata Institute to do my PhD. Usually people go into computer science, and I was kind of like a salmon going in a different direction, opposite direction. And there was some objection, and maybe for good reason. Most of my batchmates, computer science, they're all, they're millionaires, they own companies in Silicon Valley, they've already sold companies and so on. They're really very rich people. But the calling of mathematics is its own call. That's the calling of mathematics. One feels it. I mean, there's no owl or something which comes and drops a little, but the calling is there all the same.
Yeah. You forgot to mention that you were also very talented in math.
Yeah, so there's some baseline talent is a prerequisite. Yeah, some talent is needed.
the question just struck me. If you draw a circle on a sphere and take the circumference and divide by the diameter, will it still be pi or will it be different?
I don't know. Yeah, good question. The same question, great minds think alike. So this went through my head, and while he was asking this, and I don't know, Rukmini, can you see this? Yeah, so we have to sit down and do something. So, okay, we have to do this. So his question is, if you go to the sphere, there work with a circle, but now everything is happening on the sphere, and compute the circumference and divide by the diameter. Now along the shortest path is always, I have a sphere. The shortest path between 2 points on the sphere is, I take a plane passing through the center that cuts out a circle called the great circle. I have to only go along great circles. And then using such idea of distance, if I draw a circle and take the diameter, do I get pi? Very good. Yes. Oh, so it's some degenerate case. So that's like 0. Okay, so we should figure this out. Okay, so good question. I don't have an immediate answer. We have to do some quick calculation. Yes.
So you said the definition of a circle is a locus of points equal with the same distance from a center point. What is the definition of a lemniscate in a similar way?
This is in fact, since, let's go back. I didn't quite say something, and let's go back to wherever my lemniscate was. I'm almost there. Okay, one more. Okay. This is a lemniscate. Circle had relatively simple-minded ingredients, but this lemniscate, if I take this naive definition, okay, it's a figure 8 or an infinity shaped, here's an equation, I can easily mess around with this equation. What do I mean? Take this x, replace it by 2x. What am I have? A point with coordinates 1, 2, now we'll have coordinates 2, something. I've kind of stretched, or I can compress along the x-axis. I can stretch or compress along the y-axis by replacing y by a constant times y. I can change the form of this equation by sticking in a constant. Left hand side equals 2 times x squared minus y squared. I can sort of massage this equation in many different ways, but the general shape of this curve will still be the same. All of those I'm going to call lemniscates. So there's no one lemniscate. It's like, this is kind of normalized in some way. Yeah. Okay. Yeah.
So the diameter on the next circle is of the total distance.
Yeah.
So the circumference by the diameter will be actually 2 or something.
But will it be the same if I took a different circle?
No.
That's
It won't be the same.
Yeah. So somehow, yeah.
I have a bit different question.
Okay.
So, I mean, sometime before I had read it, that whatever was proven by Pythagoras has already been written in ancient Indian texts by Bodhayan. So, my question is that is the mathematics world is trying to delve into Indian ancient texts to find if some proofs or some theorems are hidden there?
I have to confess I'm not exactly a historian of mathematics, and one can ask such questions, and it might be better to kind of rely on those who study this, going into what historical references are available, or through cross-referencing what was really known, and how much did they know, and did they know it in the way of knowing a proof for it. I am a little ignorant of such matters, historical matters, so I don't have a good answer to your question. I'm just kind of glancing it away, saying through my ignorance. I mean, people, yeah.
Can two circles intersecting at one point be considered as a special case of a lemniscate? And in that case, will pi and the lemniscate constant, will they start to look similar?
You guys can help me out. That's a good question. I will say probably, can I modify this equation in some way so that it just becomes two circles touching at a point? Can I modify? Here's the problem. Again, I'm trying to do this in my head. I don't have a good answer. It's a beautiful question. Here's a lemniscate, and here's an equation to this lemniscate. And I was telling you that I can massage this equation in a few different ways and still basically get an infinity shape. Is two circles, think of my two spectacles touching here, two circles like this touching at a point. Is this an example of a lemniscate? Yeah, here are two circles touching at a point. Touching at a point. You can. Oh, what's the answer? Put a what function? Modulus. I'm hoping all these mathematicians in the audience are going to help me out here. Yeah. Do you see it? Great question. I'm going to think about this. I can't do it in my head right now. It's possible. What's the answer? Is equal to? I see. Yeah, but remove. Yeah, because then if you remove the minus y squared, it's a question of shall we call it a lemniscate or not. The recipe is take off the minus y squared, then x squared plus y squared is x squared. This means x squared plus y squared is plus or minus x. Let's work with one of them, is equal to plus x. Take it across, then it becomes x minus a half squared plus y squared is a constant, and that's a circle. Likewise, if it's minus x, then x plus a half squared plus y squared is some constant. So yeah, it will become two circles, presumably touching somewhere here. I agree. So that would be an example of two circles touching somewhere. But the question then becomes, should we call it a lemniscate? Yeah. So it's up to us. We'll make a definition of it. Is not a lemniscate. I've not given an algebraic equation. Very good. Because you have plus or minus and this absolute modulus, somebody said modulus, the same problem will happen. Yeah.
That you are exposed to highest levels of research in mathematics. What is the most elusive and significant area of mathematics that the human intellect is not able to crack, or the human intellect is not able to reach? Highest level of significant but elusive.
There are open questions. There are famous open problems. At the turn of the millennium, mathematicians collected 7 famous open problems. They just go by the name millennial problems, and one of them has been solved, called the Poincare conjecture, but the others are yet open, and one may construe them as kind of great problems that we still haven't figured. Look up millennium problems, mathematics. P equals NP, Navier-Stokes equation, Riemann hypothesis, and so on.
There are also multiple paradoxes like Hilbert's Hotel paradox.
Hilbert's what paradox again?
Hilbert's Hotel. It's
Hilbert's Hotel. Okay, there's
paradox.
an infinite number of people coming in.
There are multiple such paradoxical paradoxes in math.
Yeah, so Collard's conjecture, somehow I keep getting asked about Collard's conjecture. It's a problem, it's very easily stated, somehow people don't know how to do it. Yeah, so number theory famously has lots of such problems which you can explain. Fermat's last theorem, which finally became a theorem in 1990s, is a famous example of such a problem. Number theory, there are these dangerous problems which are easy to explain and very hard to solve. And collapse conjecture is one such.
Yeah.
Yeah, I'm happy
Gayatri, can you read out a couple of questions?
So we have a few questions from our YouTube live stream. So one is, how does the lemniscate constant connect to Fermat's last theorem or elliptic curve cryptography?
So this lemniscate constant is intimately linked to, for example, in Hurwitz we saw 1 over n plus mi, integer plus I times an integer. These are called Gaussian integers. So in the complex plane, all these integers n plus mi, if I take the plane and I have to go modulo, I have to somehow collapse these into all these different points. Look at the styling and look at all the grids, these vertices. Suppose I identify all of them, then what's happening is this collapses and then it kind of collapses. It becomes like a donut, like a vada. That's an example of an elliptic curve. And so the elliptic curves somehow naturally come up in these kind of constants, and especially those integral, the square root 1 over square root 1 minus t to the 4. An example of this elliptic integral, elliptic functions, elliptic integrals, elliptic functions, elliptic curves, they all go hand in hand. There's an entire theory which is, that elliptic curves then is useful. People started counting how many points are there in this curve, and then that became useful in cryptography. So there is a long evolution of thoughts to get to cryptography. One may not see a direct relation of this lemniscate constant per se and some cryptographic idea. It's via this detour of elliptic curves.
Fermat's last theorem is
Okay, so Fermat's last theorem, more interestingly, the proof of Fermat's last theorem. Fermat's last theorem was that x to the n plus y to the n equals z to the n, has no solution in integers if n is at least 3. And the famous proof of this is, if there were a solution, then a mathematician by name Frey cooked up an elliptic curve which had bizarre properties. Andrew Wiles, this great mathematician in the 90s, this major one, probably the most famous theorem in the last century, proved that elliptic curves, I don't know how to finish this thought. I have to get into modular forms. So maybe saying this much is suffices. Fermat's last theorem, if it is true, then it produces an elliptic curve with very bizarre properties. Lemniscate constant is related to the theory of elliptic curves. Fermat's last theorem, if true, which is not, then if there is a solution of x to the y to the n equals z to the n, then there is an elliptic curve with bizarre properties. So in the framework of a theory of elliptic curves, Fermat's last theorem and lemniscate constant both appear. There may not be a direct relation.
Okay. Yeah, thank you, Professor. So I guess there are maybe a lot more questions. We can discuss them over coffee. So once more, I thank Professor Raghuram for the wonderful talk. So, we have a few more programs which are upcoming. You'll see a poster of a talk called Quantum Entanglement in Nature, which will be delivered by Professor Subir Sachdev on 13th July. So please join us if you can. And then at ICTS, so this is going to be at the ICTS campus at 4 p.m. on 13th July. We'll have more exciting KWK talks in the coming months. Please do join us for that also.